This is the first video for Math 107 for homework number 3. And this is on polynomials and rational functions. So the first is just practice with the definition of the word. Let me highlight these words here. Degree, the degree of a polynomial, what's the leading term, okay, and the constant. So constant, the constant is the term that's just a number and has no variable associated with it. So you can see the constants right here. Obviously this constant is 0, and here's a constant down here. Those are the constants. Now for the degree is the highest exponent, and if you have a couple variables you get to add those exponents together, but here the highest exponent is 8, therefore it's degree 8. Highest exponent is 3, it's degree 3. What's the highest exponent here? Well, it's a degree 0, because remember, anything to the 0 power is 1. So this is a degree 0. Alright, here you can put these together. Oh no, here's a 9. This is a degree 9, sorry, I wasn't careful. Right. You should write a polynomial in either ascending or descending order, but I mixed it up here and fooled myself in the process. You've got to go through and pick out the highest exponent here, which in this case is 9. The leading term is a term associated with the highest exponent. So in this case the leading term is 4x to the 8th. The constant is 12. I think that was a plus. In this case the constant is 0, but you know what the leading term is. It's 6x cubed. Here it's degree 0, polynomial of degree 0. If there was an x on it, it would be degree 1. Here it's degree 3 because it's x cubed. In this case the 4 is both the leading term and the constant, but that's kind of arbitrary there. Alright, so this is just working with the words degree, leading term, and constant. In this case you multiply the polynomials and give the degree, leading term, and constant of the result. So in this case it's sort of like aggravated FOIL. You have to go for x cubed plus 2x plus 6 and multiply 6x plus 2. Obviously the highest the degree is going to be 4. Alright, now this is a division problem. You're going to take this polynomial, and it's a long division problem, and divide by x minus 2. If the remainder is 0, then it is a root, and this has to do with the theorems that were discussed in class. So I put the x minus 2 out here, and I divide into x cubed minus x squared plus 2x minus 8, and I'll show you how to do this long division here as a review. All right. To do polynomial division, you look at the first term, this x, and you say what would it take to turn it into x cubed? Obviously multiplying by x squared would do it, so I put the x squared up here, and it's not so important to line up the terms with polynomial division as it is when you're dividing numbers. Now that you've found the x squared in terms of this leading x and the x cubed, you have to multiply the x squared times everything. So x squared times x gives me x cubed. X squared times minus 2 gives me minus 2x squared. Okay? So you find the x squared based on this term, but once you get to use it, you have to use it on both of these. Now here's the real tricky part. You subtract this line from this line. Doesn't seem too bad right here. X cubed minus x cubed gives me 0. That was the whole plan. But here, remember the signs. It's minus x squared minus a negative 2x squared. So in a sense, this becomes positive. But if you go through and change these signs, you'll immediately confuse yourself, because you'll forget whether you change the sign and you have to subtract this, or so basically you leave it that way and think about it. So we have minus 2x squared, and because it's minus a negative, it's plus 2x. That gives me, for this row, it'll be the same as 2x squared minus x. I get an x squared plus 2x here. Fine. Now I go back and say, what would it take to turn x into x squared? Well, multiplying by x. So I put the x up here. Now I have to multiply it times everything. X times x gives me my x squared. That was the plan. X times negative 2 gives me my minus 2x. Okay. Now again, I subtract. X squared minus x squared is 0. That was a plan. 2x squared minus a negative 2x squared gives me 4x. All right? What does it take to turn x into 4x? Multiplying by 4. 4 times x gives me my 4x minus 8. Subtracting will be a 0. That means this is a root. It is a root because the remainder was 0. This is another division problem. Again, a long division problem. I'm not going to do this one. What I would do here is you're missing the x term. I put a 0x. That just keeps things lined up for me better, and I do like that. Now, if you want to check out that a number is a root, you divide by x minus that number. If you want to check out negative 3, it's x minus a negative 3, which is why you divide by x plus 3. And again, you look to see what the remainder is. If the remainder equals 0, yes, it's a root. If the remainder is not 0, it's not a root. Now we're going to look at the problem in a different way. Instead of finding the roots, say we're given the roots. And we need to write a polynomial with the roots. If you remember with the polynomial factoring theorem, you can write the polynomial in terms of its roots. Say here's your first root, it's x minus x1, x minus x2, x minus x3, for however many roots you have. In this case, you have 2 roots. So this could be multiplied by some number and still have the same roots. So the simplest one, I'll let a be 1. So it's x minus that root, which would be minus a negative, so it's plus 3, x minus 5. You see the signs? It's x minus the root, because the root is a 0 of the polynomial. Now that, in this case, we had real roots, and that was fine. Here you have roots, and you've got complex roots. Complex roots always occur in complex conjugate pairs. So if I have a plus bi, I will always have a minus bi. In this case, I have 2i. Well, it's really 0 plus 2i, so the other one is 0 minus 2i, and everything's accounted for. So if one of the roots is 0, you can write it like that, x minus 0, but that will end up being x by itself. So x minus 2i, and the other is x plus 2i. And that gives you your polynomial. And of course, that can just be written as x. Okay, this is the Descartes rule of signs. You will never have to do this on a test. This is where you have to do it. All right. The idea behind Descartes rule of signs is you look at the polynomial and you count the number of times that the sign changes. Okay. 5x to the 5th. I'm going to write it out here. 2x squared plus x minus 1. What constitutes a sign change? All right. This is a plus, this is a positive sign, it becomes a negative sign. There's one sign change. Negative to negative, no, that's no change. Negative to positive, here's another one, here's another one. Total number of sign changes for this, you've got 3 sign changes. Right. Then you go back through and you put a negative x in. But you've got to work out the arithmetic too. Minus x to the 5th, minus 3 times minus x cubed, minus 2 times negative x squared. Be sure to use parentheses or you're going to get mixed up. Alright, now if I take a negative and I raise it to an odd power, it remains negative. The negative sign stays. So this becomes minus 5x to the 5th. Here you would still retain a negative sign because the 3 is an odd number. So negative, negative, you get positive 3x cubed. Now if I square a negative, the sign goes away, so this is going to be minus 2x squared. Negative next to a positive is negative x minus 1. Okay, so now I've worked that out. At this point, I go back and I check out for those sign changes. Negative became positive, there's 1. Positive became negative, there's 1. Negative became negative, no. Negative to negative, no. So in this case, there's 2. And this is the place you would write in this expression right here. Whoops. That's what goes in this spot right here. Right. So now you know that you had 3 sign changes here. These are the number of sign changes. Whoops, should have written it here, I guess. I usually like to write it out there. Okay. Okay, there you go. And 2 for that one. What's the total number of roots? If you're raised to the 5th power, there are 5 roots. There you go. Right. Now, the fact that there is a number of sign variations for p of x is 3 means the maximum number of positive real roots you can have is 3. You could have fewer, but the maximum is going to be 3. The maximum for the negative is the 2. It came off of the sign variations for p of minus x. Now you could have fewer, but you can't have, like for example in the case of 3, you can't go 3, 2, 1, 0. Of course you can't have negative roots. You can only decrease by 2. Why is that? Because the slack is going to be taken up by the complex conjugates, all right, and they always come in pairs. So you decrease by 2. So another possibility would be I have 1 root, positive root, and let's look at all the combinations. So I could have 2. All right. Now how about the positive? Can I decrease again? No, because that would be minus 1. So either you're going to have 3 positive roots or 1 positive root. You won't have 2, you won't have 5, you won't have 0, 3, or 1. Now for the negative roots, we'll put this up here, you could have 3 or 1. For 2, you could have 2 or you could have 0. But that's it. So let's look at that combination. So you make all the combinations here. 3 and 0, 1 and 0. Now you have to have 5 total, so like I said, any slack gets taken up by the complex roots. 3 and 2 made 5, you're fine, you don't have any complex. Now here you have 1 and 2, that's 3, but you need 5, so here you're 2. Here you've got 3 and 0, oh, you still need 2. Okay, and this would be 1 pair. 1 and 0, you need 4 more roots, and they would have to be taken up by the complex conjugates, 2 complex conjugate pairs. And that is Descartes' rule of signs. There's a big, stupendous proof about it that's not covered in this algebra class.